This is the experiment of photodiode in which we have to calculate the phase response and magnitude response. This consists of LED, photodiode, alligator wise. Now the first in this consists of two circuits, and first circuit is made up of LED, which gets input from the signal generator and which is connected to alligator wires, and the coming input generates light in LED which comes out of it and falls upon the photodiode which is in the second circuit, and photodiode is connected across 5 volt with the help of breadboard module, and it receives the signals from it and gives the output through the alligator wires, which is also connected to oscilloscope, DSO, and also input is taken from the LED which is also connected to DSO, and we will check channel, and channel 1 is input and channel 2 is output. Here we will measure the VPP of C2, VPP of C1, and the frequency of the channel 1 and the phase difference between these two input and output. As we change the frequency value in the in the signal generator, we will get the change in value of VPP, VP of C1, VPP of C2, and the phase response. From these, we have to calculate the gain, that is V output upon V input, and we will have to plot the graph between gain and the frequency and the phase and the graph of phase response.
Readings of the photodiode which we have taken from the lab, from the experiment. This is the frequency, and this is the V output, and this is the V input in millivolts, and this is V input in volts. And from that, gain is basically V output by V input, and we have taken phase in degrees. As a standard unit of phase is radians, we have to convert it phase in radians, and this gain is unitless, so we have to convert in dB. That is, gain in dB is equal to log 10 to this value. Now we have calculated frequencies from 1 kilohertz to 25 megahertz, and based upon that values we have calculated magnitude response. Magnitude response is basically the graph between gain in dB versus frequency. As the from the graph we can understand that as the frequency increases, the gain gradually increases, reaches the maximum value, and slightly decreases, remains like constant, and increases, decreases, and remains like constant. And we have to calculate 3 dB cutoff. That is, when the maximum gain is at 2.78, which corresponds to 15 kilohertz. The 3 dB cutoff is basically means, from the definition, frequency corresponded to maximum gain divided by root 2 according to definition, so that the maximum we got 2.7, and when we divided by root 2 we got the value 1.97122, and that is between the 23 megahertz and 25 megahertz, which is written here, which is here. And the second graph we have to plot phase response. That is, generally phase response is generally a graph between phase in radians versus frequency. As we have taken from 1 kilohertz to 25 megahertz, the graph comes like increasing, reaches the maximum value, decreasing, increasing, decreasing, increasing. This is the graph of phase response, and this is the graph of magnitude response, and we have shown the 3 dB cutoff.
The experiment of a piezoelectric sensor, in which we have to calculate the magnitude response, phase response, resonance frequency, and the quality factor across each resonance frequency. This experiment consists of a speaker, a piezoelectric sensor, a DSO, and a signal generator, and a alligator wire. The experiment goes like that: the input is coming from the signal generator, is going to the speaker, and the output from the speaker is collected by the piezoelectric sensor, and that output goes to the signal generator, which is through the channel C2, and the input from the signal generator, which is given to the speaker, is also connected to the DSO as a channel 1.
Signal generator, we are giving input to the speaker, and connecting output through the DSO, piezoelectric through the DS connected to DSO. Now we are changing the frequency so that we are measuring VPP of C1. C1 is input, C2 is output, and so that the output and input frequencies changes and the phase of the graph changes.
The experiment data of the experiment piezoelectric experiment, in which we took the reading from 100 hertz to 10 kilohertz, and VPP C1 as the input, VPP C2 as the output, and the phase difference, that is C1 minus C2. From this we calculate the V, that is gain, V output by V input, and gain in dB, that is log base 10 of the gain, and the phase in radian. From these data we plotted the graph of magnitude response, that is between the gain of log base 10 versus frequency. In this graph we got the sum of the peak at the highest relatively higher value. These are the resonance frequency, and we calculate the resonance frequencies corresponding to these highest value, that is one is around 300 hertz and one is around 1 kilohertz and 1.4 kilohertz and 2.5 kilohertz, and these are the corresponding gain to these frequency, and we calculated the quality factor. The quality factor is resonant frequency upon delta f. The delta is f is one frequency succeeding to that and one frequency preceding to the resonant frequency. We calculated the differences of those succeeding and preceding frequencies, that is f upon delta f. And the second graph is phase in radian versus frequency, that is phase response. We plotted the phase in radian and versus frequency. You can see that there is a sudden change in phase, that is because of that is around 3 radian. This is you can say as I tell you in degrees, the phase difference goes from 0 to 180 degree. Further 180, if it goes to 181 degrees, the oscilloscope does not shows the 181 degree, it shows the minus 180 degree. So in radian it goes to around 3 radian to minus 3 radian. So that's why this is a sudden change in the phase.